Hey everyone, welcome to the first video for section 7.8 in the textbook where we're talking about repeated eigenvalues. So this is probably the section that has the most sort of theoretical linear algebra involved in it, but we can kind of skirt around most of it. So I'm going to walk through like sort of the general ideas and how we skirt around that. But the idea here is we're looking at repeated eigenvalues. And the main purpose of this video is to mention the point of just because we have a repeated eigenvalue doesn't mean we're in trouble and have to do anything weird. Right, there's these two different kinds of multiplicities that are in the title, algebraic and geometric. One of them is what shows up in the equation, and the other one is what actually matters for determining solutions to ODE systems. So in this video, we're going to go through what these two different things are and how they relate to trying to solve these problems. And then in future videos, we'll deal with actually trying to solve them. So let's go ahead and jump on into it. So in this section, I'm going to have to talk a little bit about general end function systems, just because it makes more sense to talk about it in general case than just a 2x2 case. But all the examples I do at the start will all be in the 2x2 case. So how do we go about finding eigenvalues of a matrix? Well, we take our matrix, subtract r off the diagonal, and then we want non-zero solution to that being 0, so we take the determinant and set that to 0. And this gives us a polynomial to solve. So for a general n by n matrix, this gives a degree n polynomial. So in the case of our 2x2 matrix, we've got a degree 2 or a quadratic polynomial. In the case of a 3x3 matrix, you would get a cubic polynomial, or something with a degree 3. This is called the characteristic equation of the matrix. Characteristic equation of the matrix A, whatever the matrix A happens to be. And the idea is, again, we're allowing things to be complex valued. So this polynomial is going to factor completely. So I'm going to call it P of R just for the sake of writing things down. So P of R is this polynomial that we get from taking the determinant. And since it factors completely, I can write it in terms of a product. R minus R1 to the K1 times R minus Rm to the Km, where R1, R2 up to Rm are the distinct roots of P. Right, so if I have, say, r minus 1 squared in my polynomial, I'll just write it as r minus 1 squared, not r minus 1 times r minus 1. I want to just focus on the distinct roots here. Now, by fundamental theorem of algebra, which we talked about before, if I look at k1 plus up to km, this has to give me n total things, right? Because my polynomial has a degree n term, everything factors, I get this, and if you expand this all out, the first term is going to be an r to the n. So the first actual main definition here is algebraic multiplicity. So each of these Ri, each of these roots Rs, R1, R2 up to Rm, has an algebraic multiplicity. So definition, the algebraic multiplicity of Ri is this Ki from up above. The number of times R minus Ri appears in P of R. So that is the algebraic multiplicity. Now, if I could get, for every eigenvalue Ri, if I could get Ki different solutions, then I'd be in good shape, because if that happens for all of them, then I get my n different solutions. And that means we're good, because all I'm looking for here is I'm looking for n different solutions of my ODE that I'm trying to solve, and then by doing stuff with the Wronskian, that'll tell me that I have all initial conditions met. So I can do whatever I want as long as I get to n solutions. So if I could always get Ki solutions from every Ri, then I'd be all set. Now the problem that you come across is that is not always the case. So the other multiplicity we have to talk about is the geometric multiplicity. So algebraic can easily be determined from the polynomial. I should look at my polynomial for this factor, see where it appears, and then this number is the algebraic multiplicity. Now, on the other hand, geometric multiplicity we cannot see from the polynomial, and it's actually the one that matters more in terms of finding solutions. So the geometric multiplicity of Ri is the number of different eigenvectors corresponding to Ri. Now, for those of you who've taken linear algebra, the word I really want to use here is linearly independent eigenvectors, but we're going to not assume any linear algebra, not assume that we know what that means, but that's sort of what we're trying to get at here. So what I mean by different in this case is I mean that they generate different solutions to the ODE. So for example, well, let me write that down. So different means generates different solutions to the ODE. So as an example, the vectors 1, 1 and 2, 2 are not different in that sense. Why? Because C1 times 1, 1 e to the RT is the same as C2 times 2, 2 e to the RT. I'm just changing my C by doubling it or cutting it in half, depending on which way you want to go. So these guys, for varying values of C, generate the same set of solutions to my ODE, so they are not different eigenvectors. They're effectively the same one. Now, in 2 dimensions, that's all you can get. That's the only way things can be the same, is if they're multiples of each other. In 3 or higher dimensions, it gets a little strange. So example 2, just to sort of illustrate the point of this, if I look at 1, 0, 0, the vector 1, 1, 0, and the vector 0, 1, 0, these do not generate 3 different solutions to the ODE, whatever ODE that might be that solves this sort of thing. Why is that? Because if I look at C1 times 1, 0, 0 e to the RT plus C2 times 0, 1, 0 e to the RT, I can definitely use that to encompass anything that looks like C times 1, 1, 0 e to the RT, just by picking my constants appropriately. Right? If I pick C1 equals C2, I get a constant times 1, 1 e to the RT, so I can obviously sort of lump that guy in with the other two. So I get sort of, these two sort of encompass that one, so I don't get 3 different solutions. I'll still get 2 different ones, but not 3. So this now gets us back to sort of the heart of the problem here, is that if I don't have enough eigenvectors, then I don't get enough different solutions to my equation. I have to do something different to get more solutions. So one quick fact about these sort of things I've been saying so far. So a fact that is always true is that for any root r sub I of this polynomial p of r that came from the determinant of the matrix, 1 is less equal to the geometric multiplicity of r, which I'm going to write this way just for notational purposes, which is less equal to the algebraic multiplicity of Ri. So there are at most the number of eigenvectors equal to the algebraic multiplicity. There might be less though, and when it is less, we have problems. So in the distinct roots and complex roots case so far, we didn't have repeated roots. So the algebraic multiplicity was 1 always. Well, if it's 1, geometric is also 1, is then also 1, which means I have the same number of eigenvectors that I had multiplicity in my equation, my polynomial. As we talked about before, that means I get n solutions out of my n eigenvalues. So this gives me n solutions out of n eigenvalues. So it's all good here. Nothing, we don't have to do anything weird here. We can just generate solutions via the eigenvectors and we get everything we need. There are also cases where I could have algebraic multiplicity being more than 1, but still having the geometric multiplicity equal to the algebraic one. If the algebraic multiplicity is bigger or equal to, and it equals the geometric one, which means I technically have all of the eigenvectors I could possibly have, all of them exist, then we're still good. So I can still get n solutions from n eigenvalues, everything's still okay, I still get the full solutions that I want. The issue is if the algebraic multiplicity is bigger than 2, i.e. it's a repeated eigenvalue in the polynomial, and the geometric multiplicity is strictly less than the algebraic one, then we're in trouble. And we're in trouble because we don't have enough eigenvectors to give us enough different solutions to our ODE to make sure that we have a full fundamental set of solutions. So this causes issue. This means we're in trouble. We have to do something else like a repeated root case from before to try to find more solutions. And the next videos are going to go through what that process is to go from not having enough eigenvectors to getting a full set of solutions for our problem. All right, so that's the point I want to make this one, just that what these things are, how they relate to each other, how they relate to needing to solve our problem, and then the next video will actually tackle finding these other solutions. So I'm going to give you a problem to work out. It just involves finding the algebraic multiplicity of some eigenvalues. Basically, do you know what the definitions are and can you write things down? So let me put that up for you right now. All right, so there's that problem for you. Technically, this would come from a 6 by 6 matrix, but instead of writing the matrix, I just gave you the polynomial. So I want you to find the algebraic multiplicity of each of the eigenvalues for a matrix that has this characteristic polynomial. It shouldn't be too hard. Go back and look at the definitions, and you'll see exactly what I want you to write for this one. All right, so that's it here. The next video is going to look at what we do to get more solutions in the case that we don't have enough eigenvalues. So thanks a lot for watching, and I'll see you in that one.